So in this video I'm going to talk about some very special properties that water has as a result of its bent shape, its hydrogen bonding, and its polarity. So remember that water has this bent geometry, and it has a polarity. So on one side you have oxygen, which is electronegative and pulls the electrons towards it, and so you have this partially negative side, and then on the other side you have the hydrogens, which gives it the partial positive side. So it's a polar bent molecule. Now, on top of just being polar, the polarity results from a hydrogen bond. So you have a hydrogen bonded to an oxygen here. So the one electron that the hydrogen has is pulled over to this side, leaving the nucleus exposed. And so with an exposed nucleus, you have a very strong positive charge, and so therefore it is attracted to the negative side of the water molecule over here. So this is a pretty strong intermolecular force, and it's a lot of why water has some of these special properties that I'm going to talk about. So the first two I'm going to talk about are high surface tension and low vapor pressure. And just keep in mind that these are all resulting because of the hydrogen bonding of water. So high surface tension is when water acts like a skin. So if you put water onto like a greasy surface, like if you put water onto wax paper, it forms these little droplets instead of like wetting and spreading out. And the reason is because the attraction between the water molecules on the surface, because of the hydrogen bonding, creates this surface tension. It makes the water attracted to itself, so it bulges up like that because of the hydrogen bonds at the surface. And that's what surface tension is. Now, to sort of give you some cool images here, so there are bugs that walk on water, and the way that they do this is because their feet are sort of flat and they're very lightweight, and so they don't ever exert a force great enough to sort of break through the hydrogen bonds of the adjacent water molecules. Here's another image showing that same phenomenon, but with a paper clip on on water. So I think that really sort of demonstrates surface tension very well for water. Now, when we put a water into a graduated cylinder, it tends to curve up if the graduated cylinder is glass. And that's because the water is attracted to the glass graduated cylinder, making this sort of bowl shape. And remember that we call that a meniscus. However, some graduated cylinders are made of plastics, and plastics are non-wetting, sort of waxy surfaces, so there's no attraction of the water to that surface. So in a glass graduated cylinder, you see this bowl shape, but if we were to put it into a plastic graduated cylinder, you see more of the water droplet on wax paper effect, because the surface tension here and because the water molecules are attracted to each other by the hydrogen bonds. Now, another property that water has as a result of hydrogen bonding is low vapor pressure. And essentially what vapor pressure is it's the pressure of a gas above a liquid. So remember when we learned about states of matter way back at the beginning of the year, that all molecules are in motion, all particles are in motion, and what makes them a solid, liquid, or gas is how much they are moving and how attracted they are to one another. So if you have a liquid and a gas is pushing down on top of it, it's going to want to stay a liquid. Those molecules are going to be attracted to each other. So if I have a glass of water just sitting on the table, the gas or the pressure above the liquid is just the atmosphere. And so it doesn't take very much pressure to keep water a liquid. And that's why we have lakes and rivers and the ocean, because the relatively low pressure of the atmosphere is enough to keep water in its liquid state. Now, to sort of give you an idea of the opposite effect, we can think of gasoline. Gasoline evaporates very easily. If you've ever, left the gas can open in the garage in the summer when you've been mowing the lawn, or if you go pump gas and you get a few drops of gasoline on the ground, it evaporates almost immediately because it has a high vapor pressure. You need to have a lot of pressure above gasoline to keep it in its liquid form rather than in its gas form. So having low vapor pressure water is really what maintains our atmosphere. So the water molecules, and the reason why you don't need a lot of pressure to sort of keep them in their liquid state is because of the attractiveness of the molecules. Now, I'm going to talk about the phenomenon of ice, and this has to do with the shape of a water molecule. So most liquids, they get smaller as you cool them, and they become more dense. And if you're more dense, you're going to then sink. When the cooler that you make them, they change from a liquid to a solid. So the solid should be more dense than the liquid form. So for example, if we're talking about a metal, if you have a liquid form of a metal and you have the solid form of the metal, the solid piece of metal would sink to the bottom because it's more dense. However, ice floats on water. So the solid form of water is less dense than a cool liquid form. And really up to a certain point, water, as we cool it, it becomes more dense. That's why at the bottoms of sort of lakes and rivers, the cooler water is sinking to the bottom, and then the warmer water is on top. So up until about 4 degrees Celsius, as we cool water, it becomes more dense and it sinks. However, when it gets colder than that, it starts to expand and become less dense. So in the winter, pipes can freeze in houses, or if you put a soda in the freezer, it'll explode. And that's because when water freezes, it becomes less dense and it actually expands. And that's also why it floats. And it's because of its shape. So if we see here, the water molecules are sort of randomly moving around, and those hydrogen bonds are forming and breaking, and that's what allows it to flow. But as soon as it solidifies, that hydrogen bond sort of gets stuck, and because of the bent shape, we make this sort of honeycomb pattern, and that's why water expands. Now, it's kind of interesting, this sort of phenomenon does have some other applications. So if we think about earth science, we talk about ocean currents, and so what drives the ocean currents is the cooling of the water near the poles, causing the water to sink, and then the warming of the water near the equator, which causes it to rise. So this is what moves nutrients around the ocean, both up and down in the water column, but also latitude, like towards the poles or towards the equator. Now, another thing to think about is the fact that it does take a lot of energy to change the state of matter of water. Because those hydrogen bonds are so strong, in order to take water from like a liquid to a gas, you have to absorb a lot of energy in order to break those bonds and allow the water molecules to escape and become a gas. And because it takes so much energy, this is sort of what moderates our temperature. The oceans are absorbing heat energy from the sun and keeping our planet relatively cool. And so the temperature that it takes to change something's state of matter is called specific heat, and we'll talk about that in later units. So the amount of energy that it takes to melt like 1 gram is the same amount to raise the temperature from like 0 to 80 degrees. So it's kind of a crazy jump. So what kind of application does this have for us? So like I was saying, if the oceans, they absorb a lot of heat energy from the sun. So specifically, if you live along a coastline, coastal cities typically have a narrow range of temperature variation. So like in Wilmington, usually in the winter, it gets down to the 40s, and then in the summer it usually stays in the 80s. It doesn't get really hot like 90 or 100 like it would in the desert, because the ocean is essentially absorbing the heat energy and moderating the temperature. Now, the polarity of water is what makes water what we call the universal solvent. It's sort of given that name. And the reason is because it's polar, it's got a positive and negative end. When we put ionic compounds into it, it will dissolve those ionic compounds. So the charge of the cation The positive charge cation will be attracted to the negative side of the water, and we say that the ionic compounds dissociate or break apart. Water also dissolves polar covalent compounds. So the rule for dissolving in terms of polarity is that like dissolves like. So polar things will dissolve other polar things, and nonpolar things dissolve nonpolar things. So oil is considered nonpolar, so that's why oil and water do not mix. Salt is ionic, so it has a positive and negative end, and that's how we make salt water. Now, something can be hydrophobic or hydrophilic. Hydrophobic means it's attracted to water and it's typically going to be charged or polar. Hydrophobic is repelling. Hydrophilic, which means water loving, that's what's attracting. So phobia is a fear. So anything that's hydrophobic is going to repel water and it'll be nonpolar. Hydrophilic is water loving, so it's going to attract water to it. It would be something polar. So an application for that is if we think about biological applications. So in biology, you learn about the phospholipid bilayer of the cell membrane. And a phospholipid has a hydrophilic head and a hydrophobic tail, and that's what creates this sort of like oily layer that prevents water from just easily going into and out of the cell.